All right, welcome everybody to today's Ascendo Reliability webinar. This is Fred Shankleberg. Yeah, I agree with you, Michael. I was just talking about the recorded webinars and now having the ability to do certificates, and that's over at ascendoreliability.com/go/webinars. And it's the content, it's what you do with it that matters. And that is a pretty decent intro to what we're talking about today, which is reliability data. Now, I suspect many of you have been in more than one location or more than one situation where there are terabytes of data available, just numbers piled up in a database someplace, or worse, all printed out someplace in a filing cabinet or whatever. We get to deal with lots of numbers. Sometimes they're counts, sometimes they're percentages, sometimes they're Pareto, the counts of in a Pareto organization. The numbers might be probabilities. They could be, stuff like sample size calculations, but we deal with numbers a lot in all kinds of factors and facets of what we do. Some are collected deliberately for a particular purpose, and some are collected just because we always do, and some are collected just because we can. And I want to talk about some of those differences and some of what makes the numbers and the expense of gathering these numbers and doing something with them worthwhile. And there's a few facets in that. Now, numbers occur for some reason. There's usually some measurement system or collection basis or some sort like that. There's measurement error that comes into this, but there's something, so like a field return. If I'm going to tick a box saying in October we had one field return on our new product, well, that means that a customer actually said, hey, this isn't working, I want to send it back to you. Right? There's an underlying event or something that initiated that to occur. Some of our numbers are how much does this weigh, or what's the resistance of this resistor, and we make a measurement. And that number, say the resistor, is because it's a estimate of what the actual resistivity is of that component. Now, there's of course measurement error on that, yet it's the number we get represents something that we're interested in. And whether it's field returns or test results or experiments or process control, there's usually something related to why that number exists. I'll make the caveat, though, that if you're dealing with MTBF, you might as well just roll the dice or use random number generators for all the value that it creates. So we'll not talk about MTBF here much today. The key to making sure that you have the right numbers is understanding what decisions that those numbers, that analysis, that observation, that experiment is actually trying to help inform. If we're looking at field data and we want to know if we're hitting our warranty target, for example, do we need to put aside more money to cover future warranties, or do we need to do a recall, or is everything going well? We may want to know that and make adjustments in our financial systems, or make adjustments in our production systems, or actually change the product. And so at some point after a product is launched, somebody's going to ask, so are we on target? And they're making a decision, do I need to make adjustments? And so providing them with reasonable information that's data analyzed, then they can make a better decision. If the product's going really well, it frees up resources for other projects. If it's not going well, it's going to tie up some resources, whether it's money or people or both, to deal with it. And so that can be a rather important decision. Yet if we don't have a rational or reasonable way to keep track of or estimate, well, what is the field return rates? What is happening in the field with our new product? We're pretty blind, and that decision will have to rely on other than good information, good data. So part of the key to having good numbers, good data, is understanding what decisions that those numbers are going to support, or they're going to influence or deal with. And that alone, keeping that in mind, it will eliminate a whole pile of the terabyte of data that so many people collect just because they can. If nobody's ever going to look at it, why are you collecting it? You know, kind of thing. Is it worth the effort and space and time and energy to make it work? So those are some of my concept or ideas here when I'm dealing with reliability data. So we'll talk about a couple different parts of it. So what are some examples of reliability data? What would you think is meant by reliability data? Hopefully got you involved in coming to the webinar. So maybe you have given this some thought. What kind of data do you use? And I'll pause here to take a quick sip of water. Well, I did mention field data. Failure data is good. I like that. Warranty return data. Yeah. What else? What else do you pull into? Time to trip. Oh, that's a good one, Carl. I like that. Halt data. Yeah. What is the size of the margin you got on these different stresses? Manufacturer's data. Yeah. My favorite manufacturer's data, Dan, is when they have a data sheet and they put a big black box around it and they say it has an MTBF of 50,000 hours and it's 50,000. It's amazing that that can be that precise. And their product is built to be exactly that number. There's a whole story behind that. I like manufacturing test data when they actually reveal what they tested and how they tested it and what kind of analysis they do with it. Are there models? Production data, ESS, degradation data, users environment. Good. I like that, Longchun. Yeah, good. SPC, process capability. That's all in there, Kenneth. Yep, good. All right. As you can tell, there's lots of sources, and I think this crew here today is sorted out many of the ones that I'm going to mention. Although I think I've got a couple extras for you, plus a couple of stories of innovative ways to find the data that you really need. So, a couple of examples. One of them that Larry George talks about all the time in his article series is ships and returns. How many units did you ship and how many came back? And you may be familiar with the Nevada chart, which is a way to organize that information. And it's a basic one that most companies that ship products keep track of. They know how many units they're shipping per week or per day or per month. And not everybody, but many are able to isolate, well, when did I ship that? What serial number was it? And when did it come back? So we have this, how much time it was in the field. Now, it's not perfect data by any means, but it's actually very, very useful. And there's multiple ways to really extract a lot of good information out of that. And it's usually available in every organization. It might take some work and detective work within your organization to find it, unfortunately. And sometimes the bigger the organization, the harder it is to find. Yet that's where I tend to go to right away. How many units have we shipped and how many returned? And that allows us to do all kinds of things with it. Warranty data is usually in dollars. And so that usually takes some conversion as to, it's a step away from, say, the ships and returns, the counts. Yet if you only have one product or the cost of the the sales price of your products are generally the same, then warranty data in dollars has an easy conversion. Usually it gets a step more complicated when you're dealing with warranty costs, because there's the reverse logistics, there might be repairs, there might be shipping costs, all those kinds of things. Some organizations count call centers in that, some don't. One of the things about warranty data, and I know I've mentioned this many times over the years, is the site called, I'll put it in the chat, warrantyweek.com. Eric Arnhem looks at publicly available information about a wide range of companies, and he lists what their warranty accruals are, what they're reporting as how much money they're setting aside, and also how much money they're actually spending on warranty. And Eric does a really good job of reminding the readers that if I'm comparing, say, Ford and GM warranty, is that they don't count the exact same bucket of things in the warranty expenses. And they don't count the total cost of unreliability, the cost of reworking something, or redesigning something, or changing a production process. Usually that doesn't get counted. But sometimes in some companies it does. And sometimes call centers are counted, sometimes not. So comparing warranties is suspect. But comparing warranty numbers over time for a particular company or particular product line is usually insightful of what's going on. And so it's a way to look at what's happening in the field. And again, it may or may not be readily available. And depending on how siloed your company is, that may be an issue. But warrantyweek.com is a great resource to get an idea what your competitors are doing around with the trends that are happening within their own warranty systems. Customer satisfaction. One of the things that's really quite amazing is that and it's related to acquisition costs for a customer, is customers that are happy with your product, with your brand, are a lot less expensive to acquire to buy a new product. So part of the cost of creating a product and put it on the market is the cost of making your potential customers aware that it exists, what its features, benefit is, how it compares to some other thing. And the idea is that if customer satisfaction is something that your organization tracks, and you've got a good relationship with the team that's doing that, one of the things I recommend is asking, so what proportion of customer satisfaction is contingent on reliability? And just recently I was talking to a colleague, and he sent me a paper, or a link to a paper that was done in Europe, where they measured how important, how long a product lasts before a customer says it's good. And that he was working in a white appliance company that's making washers, dryers, stuff like that. And it was about 10 years. Customers said, if it lasts for 10 years, I'm very happy with that brand and I'll buy it again. Do you know that value for your product? Because if you're only tracking warranty, that's usually pretty short term. If you understand how long a customer wants that product to last, which is often longer than the warranty period, then you could really impact customer satisfaction if you meet or exceed that value. And it has the added benefit of reducing the cost of the next sale that you do on average. I'm going to talk about repair centers a bit later, but repair rates, how many spare parts are heading out the door, how many products are heading to your repair centers, for whether it's under warranty or not. There's all kinds of pieces there. Bummer, Maximilian, that the warranty week's down. I'll have to check that out afterwards and send Eric a note. He may not be aware of it, but hopefully it's up soon. He does do a bit more advertising than I like on his site, but he does have good articles and good information. And It's a free newsletter, and it's fairly regular. I'd say every 6 weeks or so, he goes into one of the industries like automotive or home building or, medical devices, and breaks down what's happening with the top warranty expenses on each of those and what's their trends. And he does a really nice job doing that. Yeah. So there must be something going on with the site over there, but I'll have to check it out and give Erica an email afterwards. But it is worth checking out, and hopefully it's up soon. Yeah. Kenneth, there's this idea. I see your note on customer follows proper PMs that lasts a good time. Yeah, that's true. It also has to be, cost of ownership can't be that I'm looking at the difference between a Toyota and a Jaguar, and I'm just doing stereotypes on this. But if the Jaguar runs for, a week, and then I'm in the shop to do a couple $100 worth of maintenance and preventative maintenance on it, versus a Toyota that could run for 5 years before I do anything to it, besides put gas in it, the cost of ownership shifts quite a bit. Now, of course, there's a difference between performance and what you're trying to do with the different brands of cars and so on. So that may be worth it to somebody. But if it's one of those things, it's always a trade-off. And knowing your market, knowing your customers is a big deal of it. There's a very big piece of that. Okay. So field data, there's lots of stuff we get from the field. The unfortunate part is that field data is looking in the rearview mirror, right? We may learn something for our next development project or the one after that. If you've got a quick turnaround, if you're making 2-3 products a year, some companies do, waiting for 6 months to get good field data might miss the next product development cycle altogether. It's too late. And so it's decent information. It's from your customers. If you're listening well, is one way to put it. Yet it's after the fact. And so we generally are looking for data during the development process when we're creating the product or setting up the production line. Is where do we get information that helps us know if we're going to meet our future targets? Now, there's all kinds of tools from guessing to testing and pretty much everything in between that allows us to get a sense, are we on track? Now, a big part of what we do in reliability engineering for product development is understanding, well, if that's a major question for us, are we going to hit our target in the future? We may specifically set up ways to collect data that helps us answer that question. And one that I really enjoy is because I've never gotten enough prototypes from any development project to really do a detailed analysis with enough time to really answer that question through testing, is I realized that even though I got a good percentage of the number of prototypes being made during development process in the reliability team, the quality folks got a pile of them. The software team got a good number of them. The mechanical electrical engineers, they had one on everybody's desk kind of thing. There was a lot of other units out there. And most teams that and this is one example, I was working with a team that when a software guy had a problem with a mechanical element of the prototype, he'd work on something else. He'd go find another prototype that didn't have that issue and would test the software on that, or would do some other unique workaround to make it happen. Yet they did not report that issue with that prototype. And the excuse I got over and over again, and you may have seen this or heard this, well, it's just a prototype. Well, it's absolutely amazing to me is that our prototypes are our best iteration of our current design, right? They're the manifestation of our current design. And we may be taking, using different manufacturing process. We may be using, instead of using hard tools for molded parts, and we use a different assembly technique for this and that and the other thing. Yet it's as close as anything we got. Now, the CAD drawings and the SPICE modeling that we do and all the other stuff we do is our digital version of that. Yet it doesn't include manufacturing errors. It doesn't include, variation in parts that create the lack of clearance or too much clearance or things like that. So when a software person notices something that's a mechanical, electrical, or some other issue with the product, it took some training and encouragement for them to say, hey, hey, Fred, there's an issue here and it's not my job to fix it yet. Somebody should or be aware of it. It's not like we fixed everything. There's no way. Yet what we did is we gathered probably an order of magnitude more information than we would have gotten just from the samples that we had in the reliability and quality teams. And it really helped guide us as to where the priorities were, what were the types of things that we needed to focus on. And it also helped reinforce what we were already suspecting was going to be an issue or not to be an issue. So one piece of advice is if you're in a development team and they're handing out prototypes and they're usually expensive and they're usually scarce to other parts of your team, and even to the ones I don't like the most is the when they give them to sales reps and they take them off in the back of their car and bounce them around highways and then wonder why it doesn't work. But the idea is that there's a lot of information out there, whether it's manufacturing problems or it's design issues or all kinds of stuff. And usually they're not under a lot of stress, well, except for that sales guy that I mentioned. The idea is that there's all kinds of data available, information available, I should say, from those prototypes when they're distributed across your organization, if you have a process to listen to that, to gather that information. Now, of course, we have testing, right? We have got all kinds of testing. And I was just recording a podcast the other day with Kirk. And one of the ways that we really don't like testing in reliability is when you have no failures. Not necessarily a full-on halt where you're forcing things to go at this. It's more along the lines of, if I'm going to follow a standard, say, for an environmental test, and they say, X number of samples at this temperature for so many hours, and nothing fails, well, what do you know? What's the acceleration model? Well, the standards typically don't tell you that because they don't know what your product is, what your materials are, and so on. So if your testing is set up to actually provide information to inform decisions, it goes back to that theme I'm going to probably hammer a little bit too often. You can get really good information from your testing, good data from your testing, if that test is set up to generate good data. And we'll talk about that some more. Let's see. Robert mentions, isn't that what a FRACIS system does? Yeah, collect failures in every source possible. That works great when it's more than just two mechanical engineers feeding information into it that are blaming the electrical guys or software guys, and vice versa. Or the software people only put it in when it's a software related issue for that other module over there that Sarah's working on. It does take some training to say, if that paper jams in a printer, it may be electrical, it may be software, it may be clearance or manufacturing issue, it may be electrical, who knows? But notice it and write it down. And that's, yes, a good FRACIS system will really help to do that. Now, there's a whole other podcast about FRACIS systems, or webinars, I should say, of how they can run amok. And so just one note on that is that one of the biggest hurdles I've seen to FRACIS systems is that if you report it, you fix it kind of attitude. And which is really a dampener on people actually reporting stuff. And if they don't report it and nothing good or bad happens and they can continue on with their day, it's great. The best systems of FRACIS is when somebody reports it and it gets resolved, or it's deemed it really is just a a fluke of the manufacturing adjustments or workarounds we're doing, and we have to deal with it. Yet the best ones are where it gets prioritized and sorted out and resolved, and it doesn't place a burden on the person reporting it. It actually ends up being an advantage to them. There's all kinds of, well, there's way more ways that it can go wrong, and good practices with that. But let me pause for and say that's another subject for another day. Simulations and models. I just got the question yesterday from a listener or reader that was talking about, can I use simulations or when I have scarce amounts of samples? When I don't have enough samples, can I use techniques to simulate, using simulations, for example, or modeling, for example, to get more information out of it? Yes, you can. And the first thing that came to my mind is, if I only have 10 samples and I need a really good estimate of variance, well, there's a statistical process called bootstrapping that is made for that. It's a computer-intensive modeling technique, well-founded. It's been around for decades, and it helps you get a really close to or perfect, as close as what the population has, estimate of the variance. And we need variances for all kinds of things, for making comparisons, for setting limits, for all kinds of stuff. And so getting a really good number for that, even when you have few samples, is really a boon of the power of simulations. But other things can help, like finite element analysis and physics of failure models, which I think I have on the next slide. Let's see, David's mentioning success testing, zero failure testing. I've also heard it called bogey testing, compliance testing. They don't teach as much, just the snapshot of performance. Yeah, my favorite by far, my poster child to beat up on, is the 85 Celsius at 85 relative humidity for 176 hours or 1,000 hours. Various standards use different times. And so you know that it works at a chamber at 85 C, 85 humidity for a week. Okay, so what? What was it supposed to catch? What was it supposed to tell me? If I do have a failure, how do I interpret that? Was that bad for the first week of product life, but we're not in that environment? What does it exactly do? Yet standard after standard doesn't really help you interpret, well, what's it for? What failure mechanism am I actually evaluating here? And how do I interpret results out to the real world, into various real world environments? Now, if they don't cover those criteria, it might be a perfectly good standard of how to set up and make sure your chamber is working, and roughly how many samples you need. Yeah, what else is it really useful for? And so there's a bit, I look at some of those standards, especially environmental testing standards, as being suspect. It's got to help you understand what you're trying to achieve, where is it useful, and how do you interpret the numbers when you get them out. And success testing is so economical. I get to minimum number of samples. Well, that's great. So there's two problems with it. One is, let's say I get 22 samples and I'm going to 90% reliable at 90% confidence. I'm trying to check for that. And if all 22 samples survive what we consider the duration for this test, then we can say that we're at least at 90-90. It's good. If we have a failure, there's no conclusion from this test other than that we can do some failure analysis and maybe go fix it. Yet there's no, if you start fussing with the numbers afterwards, then the basic hypothesis, does it meet this minimum criteria, is no longer valid. It's not there. Yet how bad is it? We don't really know. So you just have to keep running the test till you get more failures. The other part is, if they all pass, yeah, you can claim you're at least 90-90, but you don't know how much better you are You also don't know if that test was actually plugged in or not, whether it gave you a appropriate set of stresses to represent the life of your product. Was it actually evaluating the right thing or not? If you get failures, at least then you know that you've excited some failure mechanism, can do some more work on it. If we expect this to be the first failure and we flip this switch 28 times or whatever the life expectancy for that switch is, and nothing happens, was that just a particularly good set of switches, or were we lucky? Or was it actually a good design? We really don't know. We haven't learned much of anything. Yeah, you're exactly right, Bert. Is this, what's the failure modes? What's the failure mechanisms at play on this? And getting reasonable information, not just a number, yes or no, or binary, stuff like that, but what's actually happening. Ken's mentioning corrosion. I think that's, it's what I find in success testing is that you can double the samples and cut your duration in half. And it's underlying it. It's making this assumption that that every hour under the test is equivalent to so many hours in the field, or if it's accelerated or under, the same set of conditions, it's essentially saying a constant failure rate. If it's a corrosion problem and you're doing a success test, each sample needs to run long enough for the corrosion to actually occur. So it goes back to this idea is that if I'm going to go collect some numbers, if I'm going to run an experiment or run a test, I really need to understand what I'm trying to achieve. What do those numbers really represent? And will that be informative to a decision that this is intended to support? I think like I said, I'm going to talk about that theme quite often. A whole bunch of other ones, a couple of them we mentioned, but one I didn't mention yet is literature. Oftentimes, the very first step when I'm working with somebody on, say, an accelerated test is, do you have a model for it? Is there a good way to translate the accelerated conditions to use conditions? Because if so, we can really streamline the test and it'll be quicker, less expensive, all those kinds of things. But if we don't have a good model or good way to make that interpretation, well, then we need to create it. And that takes time, and usually more time and more samples than anybody wants to use. There are just about every material that we use in our products, in our systems, in our factories, has been studied at one point or another by a whole crew, usually university folks. Sometimes companies, when they do their own research, they publish it. And they often talk about its durability or its reliability aspects or characteristics, or tensile strength, if nothing else. And that information in the published literature is a great starting point to understand, how does this thing fail? How does this failure mechanism behave? And so a real common first step when I'm looking for data is go to the literature. Is somebody else has probably already studied this, and let's go find out. Now, if you're in a company that's inventing new stuff, well, go talk to those scientists. Are they looking at the aspects of that new material or that new element or new design in a way that would create information that's related to, say, an acceleration model or time to failure models or physics of failure type models? There's probably something out there. And the hard part is knowing if it's close enough to be useful for you. Yeah, I am, Ken. The 8585 damp heat test, yeah, it's okay for corrosion under certain circumstances, right? If the corrosion has to get through a barrier, or the humidity has to get through a barrier first, did we do thermal cycling first? That would strain the adhesion, say, of a barrier. But all too often, it's throw it in a chamber at 85 for so many hours, not even powered many times. And if it comes out, it's good. Good for what? Is what I usually come back with. Yeah. A good, Robert, a good website to find acceleration models. I don't know if it's still out there. It was called not WARP. Yeah, it was WARP, WARP. I think if you Google WARP physics of failure model repository or something like that, it was a part of the crew that came out of the old Rome laboratories and a couple other ones. Yeah, and JEDEC has a couple different ones. There was a bunch of work by Laurie Bechtold out of Boeing to collect models that were relevant for the aerospace industry. And it was with some standard body, and I'm drawing a complete blank to them. There's a handful of different ones out there. Yet be very careful, because the models for, say, 10 nanometer may or may not apply when we get down to 3 nanometer. Which ones are appropriate for which type of system you're dealing with. The BUs, the recertification units, you mean, Deshita? This is an aside from the topic, but the idea is that if you grab a screenshot or print out the title abstract when we advertise the event, that's the topic and date and time and all that other good stuff. And within a couple of days, the Zoom system is supposed to send everybody out an email that says, thanks for attending. That's your proof of attendance. So those two things put together usually satisfies folks in the ASQ certification group and other professional development folks. And that alone is good enough for it, for vast majority of webinars and most programs. And I think we talked last week about how to get the sort of certificate of attendance from the webinars on the accendoreliability.com/go/webinars. But whatever works for you. But usually people just use what's the abstract, title abstract stuff plus the thanks for attending. Let's see. Back to the acceleration models. One advantage I have as being a lecturer with University of Maryland is I get faculty access to the library. So I can search across the technical repository of articles. That often finds something. And then I'll just write to the author, and send them a note saying, hey, I'm looking at this article. Is this appropriate in this and this circumstance? Or how would I extend this to work over here? They often have thought through that already. And I get information that way. Another place to search is in sites like ResearchGate. And there's a few others similar to that where people share their work outside of, say, library paywalls and stuff like that. Another spot is go to LinkedIn. We've got a lot of peers out there that know a lot of stuff. Ask them. Anybody got a good model for corrosion of XYZ material? You might be surprised that somebody's got one and is very interested in helping you on that, because it might help their process. But we can find all kinds of information, including just the expert opinion of, well, how long is this thing supposed to last? Now, if you ask 10 people, you'll probably get 10 different answers. And it's called the Delphi process or method. And then you take the highest time to failure estimate in the lowest ones. You go back and ask them, why did you say this? Maybe they have some insights. Maybe it was a flat out guess, but ask them to support. Why did you make that estimate? And then share that back with the rest of the group and ask them again with this additional information, what's your estimate of it? In 2 or 3 rounds of that, you'll usually come not to a consensus, but to a pretty good central point. And over time, that process is actually shown to be pretty accurate, is in all kinds of stuff and time to failure information. But you have to talk to the right people that have some information or some knowledge about, well, how long is this material supposed to last in different environments, for example. Let's see, got a question on finite element models capture mechanical failures in all particular data, parameter data. Maybe. Depends on how you set it up. One of my favorite examples with finite element is I saw a circuit board that was mounted on an edge connector, and it was basically a big diving board inside the product. And they said, well, it doesn't have very far to move, and given the material characteristic of the circuit board, it's only going to bend here, and we minimize the components and everything else that's in that area. It should be fine. All right, great. So we sent it off to finite element analysis. What happens if this thing is dropped, which is a handheld product? What happens then? And they came back pretty quick with a simple model that said, oh, it's going to do this more complex motion. And where the highest deflection was happened to be right under the crystal on the circuit board. Well, crystals don't like being bent. And we found in drop testing that the crystals broke. And the mechanical engineers completely dismissed this third-party finite element analysis. And oh, they made too many assumptions. Oh, they don't have their insights. They don't know what they're doing. And then we showed them the failure data from actual drop tests. And then we got a clear case on this thing and did high-speed cameras and showed them the actual motion that the circuit board did predicted by the finite element analysis. Then he finally said, okay, I'll fix that. It was some of the parts of any of these models is not just finite element, is they're approximations, and there's tons of assumptions that go into these things. So being very clear on those and being very good at getting good models, good representations of what's going on, your biggest battle is to be convincing others that you're on the right track. You might not always be. There's no doubt about that. Yet the models can help in so many different circumstances, and we can minimize the amount of testing to validate the modeling versus trying to do testing to create a model if we already have one in existence that we can use. But finite element is a great tool. And one of the things I used it early on with is that, well, you're doing all this finite element for how this thing moves or vibrates or things like that. What happens if that material ages a little bit and it becomes a little bit stiffer? Oh, I haven't tried that yet. He was using the factory settings basically for the materials, modulus and things like that. And they're like, well, how about we age it a little bit? What happens to its ability to absorb this motion? Oh, it changes. All right, well, let's put it in the model and change it. And that became a serious problem. And he said, oh, we got to fix that, kind of thing. Finite element can do current conditions, but if you think through it, you can change the properties and parameters of it so that it's aged product and without having to put it in a chamber. Again, lots of assumptions there, right? Yet it's worth a look at a way to avoid having to age it for 6 months before you run the next test. You can do it in simulations sometimes. So where do you find data? I think we mentioned a whole pile of sources up there earlier. Within your organization, our test labs is one place, across the development team or across the plant floor is another, a great big database that's collected on all your field data. We have lots of different places to go look. So I'm going to tell a couple of quick stories here about where I found data, where I've run across people finding data. So one of them was a product that was actually been in existence for, 15 years. Each year there was just very minor changes to it. The product and the way it worked and the way it felt and how it operated was so contingent on it being consistent. So if you picked up one game controller versus another one, they behaved very, very similarly. There were modified changes to the colors of the outside. Sometimes, a vendor would go bust for some part, and as though they'd put a new part in it and slight change to the circuit board, things like that. There were some speed and reducing latency type things that were changing, yet the fundamental product itself had changed very, very little. And I was working with this team on a new product, and they were looking at, well, how are we going to do ongoing reliability testing for this? Hey, Fred, you set this up. And what they recommended was essentially all of the qualification tests that they were doing at the end of the design process, which was 28 tests. And I said, do you do this on all your products? Oh, yeah, we do it all the time. Well, where are the results of those? We can really figure out which tests are useful or not useful if we have that data. And they all looked at me with a blank stare. Well, we don't deal with that data. We're working on the next product. Okay. So to make a long story short, it took me 3 months to find the person that controlled the data, where it was in a basement. I'm quite sure it was a basement of some factory building in far off someplace where these people were manufacturing these things. And I said, and he was saying, oh, this is great. I can do this. How do I get this to you? There's a lot of data, maybe we'll break it up. And he says, has anybody ever asked you for this data before? He goes, no. And he's, how long you been here? 14 years. All right. Well, I don't need all of that. I need the ones for this product line and this family of product and so on. And he goes, oh, okay, great. And he shipped me all kinds of information. Well, it turns out of those 28 unique tests, 27 had CPKs like over 10, over 12. They rarely ever even came close to any of their criteria of what was good or not good. And why they were testing these for decades was beyond me. One of them actually predicted every major field issue they had. And because I did have access to the field data. And it's like, these all are similar issues. And they had one test that was about a 2-month lead time predictor for all of those issues. And so they ended up producing products for 2 to 3 months that were bad. And before the field data amounted to enough that they went and did something about it, as opposed to actually paying attention to the tests that they were paying to have done every month that actually predicted those issues every single time. It was amazing to me how little they looked at their own data. So in this case, it was just a rumor. Oh, we do a lot of manufacturing testing, right? Do we have access to that data? Can we get to it? Sometimes it took some real work to get to it, and it may or may not be useful in your part of the world, but it was a gold mine. Ended up saving them $250,000 a month, basically. I don't remember the exact details, but it was well worth the effort to have found that data and make some changes to how they did their testing and also how they paid for their testing. So that's one of them, is where do you do your manufacturing and what are they measuring, whether it's on the production line or whether it's in ongoing testing or if it's in end-of-line testing. Those are all good sources for detecting what's going on with your product or not going on with your product. Spare parts. Years and years ago, there was a question that came up in the team I was working with that said, which of our cooling fans that we put in servers are better? And which one should we use and which one should we buy more of and which one should we buy less of? Well, that seems like a reasonable answer or question, but we didn't have that number. We knew that X number of servers had fans repaired, but it wasn't real clear as to which vendor fan that was. So what would you do? Right? Well, we dug a bit deeper, and a colleague of mine found that at different points in time, what they would do is the production line would get basically a pallet of vendor A's fans. And so for these serial numbers, that vendor's fans went in those parts or those servers. And then the next quarter, another pallet would show up and they'd put in a different vendor's fan. And it was kind of the procurement guys of, buying from 2-3 different vendors in order to negotiate better prices from all of them, kind of stuff. And so with a bit of work and some more SQL search capability than I ever figured out how to learn, my colleague was able to find out, which servers by serial number had which fans. And then the repair data, we also had the serial numbers. So we were able to to sort out which servers had which fans, and then we knew, which ones were being repaired for that. Plus, he found out that if I just look at the spares, how many parts of that pallet were set aside to be for spares? And there was a regular sparing algorithm being done in this warehouse that support all the repair centers. And it turned out that that number in the production or in the repair reports was pretty confusing, because they often repair a bunch of different things, not just fans. And sometimes they wrote down, they replaced the fan, and sometimes they didn't. What we did find is that the number of spare fans that these repair centers would actually buy, because they didn't buy it just for fun, they bought it when they didn't have any more of that particular thing. And so they were using that. So we ended up using the data of how many spares we were shipping out. And that ended up being very, very clear that the difference between our best fan vendor and the worst fan vendors was night and day. Think of a really stark Pareto diagram. But it wasn't field data directly. It was like 3 steps away from it. And the systems were set up for doing, how do we pay for the repair centers? How do we do return authorizations? Because it just doesn't work. We don't know why it's not working. We knew that the repair records were pretty noisy, and yet we're able to find a reasonably good number that we could use and had good evidence that it was a rational number, was how many spare parts were being shipped out, how many fans of the different vendors were they buying. Because it was one of these things where you couldn't swap one vendor's fan for another one. There was a different bracket that went into the system, so that if you it cost a lot more, and it was a lot more work to replace that bracket than it was to replace the fan. So it was all kinds of things just fell in place that we could use spare data. So it's another unique place to look that I ran into years and years ago. Robert, did he have a red stapler? I never met him. I wish I did. He maintained this database, collected all the data, kept it all sorted out and organized by product line, by all kinds of stuff. And he was so happy that somebody was actually going to go look at the data. Apparently that rarely happened. So it's an interesting, I don't know whether he had a red stapler or not. Repair centers, 2 stories here. One of them I ran into was a company that made cameras, and they're expensive cameras. And so when a camera got shipped back to the company to get repaired, the repair center within the organization prided itself on how quickly it could do the repair. Now, they essentially just rebuilt all the guts. They pulled everything out, put all new stuff in it, and shipped it out. And usually within an hour of it hitting the floor. If it came in the morning, they tried to get it on the truck going out that night. They were really good at turning stuff around. I said, and I remember sitting down, and it was the vice president, and I said, what would happen if you didn't have so many repairs? Oh, I'd have to fire people. I'd have to, do all this stuff. No, I mean, not you and you're part of the organization. What about to your customer? What if they didn't have to send you their camera for a repair? What would that do to future sales? What would that do to customer satisfaction? What would that do, to your brand? All those other good things. And he used actually, it's a valid argument. He said, remember Dell, when they were first doing all their customer support and stuff, and it was just exceptional. And they found over and over again that if you had a failure, you became a more loyal customer to their brand than if you didn't have a failure. I said, all right, do you have any evidence that that's working in your case? And I also knew that their market share was decreasing over the last couple of years and things like that, because other companies just made products that didn't fail. And it was a real hassle for where this camera was being used and how it was being used for customers to replace it, to put a spare in place, or to do without for a while. I said, that worked for Dell. Do you have any evidence it's working for you? Because your market share is going down, your profit margins getting smaller, blah, blah, blah. Oh, so what should I do? He says, how about when you actually do the repair, you figure out what actually fails, you have the capability of doing it, and provide that information back to the development team so we can actually fix it, so that you end up getting fewer repairs. And he goes, oh, I got to think about that. And they ended up hiring a handful of people and getting a really nice failure analysis lab in there in order to extract way better data from those returns, such that it created a cycle of reducing the number of returns that were occurring, instead of trying to go ever faster at turning turns around. And so part of it here is what do you focus on in the different parts of your organization? And many of you heard me rant about the procurement organization always trying to reduce the cost, as opposed to paying attention to what the warranty or field returns are. But if we don't have good failure data from the field, for example, it's really hard to argue with the procurement folks that are saying, hey, our goal is to minimize costs, right? Well, part of your cost minimization is increasing warranty, which is more than replacing the benefits you're getting. So how do we get the data that balances out? And we've all heard about balanced scorecards and KPIs and all that good stuff, but that's part of this data discussion. Do we have the right data to balance out and motivate our organization to reinforce and get good reliability out of their product? The other story I had, and it's a real quick one, is we were wondering why is these servers again, why is the CPUs failing so much? It is a complex part. We're really pushing it hard in this application. It could be possible. Well, it turns out there's nothing wrong with the CPUs. We were getting, 70, 80, 90%, no trouble found when we got them back to the labs. And we're like, what? We just could not figure out what was wrong with these. Well, it turns out the repair guys that went out to these facilities to repair and restore the server banks that were being run, is they got paid a minimum rate just to be there, their travel time basically, and a percentage of the components they replaced, the value of the components they replaced. So if they would open a tray and reseat a couple of connectors or change out say a power supply board, they made enough for lunch. If they replaced the main CPU board, they made enough to make it worthwhile for their entire day, and their day was done. They made enough money for the entire day, even though the CPU had nothing wrong with it. And talking to the repair folks, it says, if I'm going to open it up and reseat all this stuff and do all this diagnostic and do all these resets, which I don't get paid for, I'm going to replace the motherboard because it's right there in front of me. And part of resetting all this stuff is basically handling it. So I take it out, put a new one in, just in case it is the CPU, because I don't have good diagnostics. It's not running. So I will replace it, put it all back together. It's working. Now, was that reseating a connector or restarting it, or was that a new CPU? I get paid if it's a new CPU. I don't get paid if it's not. I'm like, we might want to rethink that contract. And so always second guess where your data is coming from. What is the motivations behind it? Why is it created the way it's created? And there's lots of richness that can be found in all of those kinds of things. So real quick, what makes good data? We don't get perfect data. Just get over it. We're just not going to get it, right? If we understand how it's created, how it's measured, what measurement errors involved, what are the motivations for why it's collected or not collected, and is it on time? Do we get good information as to, is it reasonably telling us what's going on? That's great data. It's about as good as we're going to get. Putting onboard diagnostics that, really tell you a decent system and send it back to the mothership all on its own. We don't do systems like that often enough. it's really, really useful when it can happen. But the hardest part about this is that, and it goes right back to what I started with, is that it's tied to a decision. Now, you see this more on manufacturing lines. Just because I can measure these 57 parameters over a production line, do I really need to? Which one is actually going to provide us information that we're going to make a decision with and do something about? Or can I turn on and off these various ways to collect data so that I can focus on a particular area and not spend the money of actually collecting and storing it? If I've got a terabyte of data, where do you start, right? Yeah, we're getting better at dealing with large stacks of data and maybe feed it all into ChatGPT. The idea is that other than for the joy of exploring a big stack of data, it has to actually lead to something useful. It costs us money to collect data. It costs us money to store data. It costs us money to analyze it. If I'm trying to inform a decision, I'm starting with the end in mind, right? What am I trying to understand or model or estimate or whatever? What data do I need to do that? And then go collect it, as opposed to collect everything and hope you got the right stuff. I find that rarely works. Bottom line is that the data that we help to create, or the data that we look for within an organization, should really have a return on investment. It should actually be estimated. What's the value of this data before I go collect it? And then go measure it after the fact. What benefit did having this information actually make? Doing that on a repetitive basis really avoids that collecting data just because, or collecting data that we might need maybe someday, hopefully in the future, and wasting gazads of data, time and energy for stuff that really is not useful. We find out too late that it's not meaningful for us. Let's get the right data and make sure it really makes a difference. So I think that's what I, last question. It's rhetorical unless you want to dive into it. But I'm quite sure each of you can come up with a story of where the data you collected really made a difference. And I'm quite sure you could also come up with stories of a whole bunch of data that you collected that really didn't go anywhere. And I'm guilty of that, definitely. So anyway, any comments or questions, that kind of stuff? I appreciate all the comments throughout, all the input and so on. I got a good, nice chatter going on there. But that's my 2 cents worth, or 58 minutes worth of rant on reliability data.